Thanks very much, everyone, for coming to the seminar. It is my great honor to be able to introduce Professor Masaru Shibata. Professor Shibata is one of the director of one of the divisions of the Albert Einstein Institute in Potsdam, and he's also a professor at the Yukawa Institute for Theoretical Physics in Kyoto, Japan. And so, without further ado, please.
Thank you very much. So it's my great pleasure to give a seminar in person. So this is a first in-person seminar last 2.5 years. So I believe that the last seminar was given at the Copenhagen, so 2.5 years ago. So today I would like to talk about the latest progress of numerical-relativity. In particular, focusing on the astrophysical side, like neutron-star merger and stellar collapse to black hole. Okay, so this is the outline. So I will give a brief introduction about the numerical relativity and the neutron-star merger first. Then I will talk on the neutron-star merger and related nucleosynthesis for heavy elements. And if I have a time, so I would like to introduce our latest discovery by a numerical relativity simulation about supernova-like explosion and collapse to a rotating black hole. Okay, so let's start from my introduction. So first I'll talk about the numerical relativity. So perhaps as you know well, so numerical relativity is just a field in which Einstein's equations are solved by computer. It's now an inevitable tool in gravitational physics and the general physics, astrophysics. So, for example, this is shown, for example, for the case of a gravitational-wave astronomy. So for preparing theoretical templates of gravitational waves, numerical relativity is necessary, and great success has been achieved. In particular, for binary black hole merger, I mean that to detect the gravitational wave from to extract detection gravitational waves and to extract the information of physical parameters from detected gravitational waves. So we need a theoretical template, and so to construct theoretical templates, so numerical relativity is now necessary. So it plays a great role in the gravitational wave astronomy. And so numerical relativity plays an important role for modeling electromagnetic signals of high energy phenomena like neutron-star merger and the stellar collapse. So I mean that associated with, for example, neutron-star merger, people observe the electromagnetic signals, and for interpreting the for example, light curve of electromagnetic signals, we need some template, and so for developing a template, numerical relativity plays an important role. And also so it plays an important role also for predicting a new phenomena in astrophysics and cosmology and gravity. So numerical relativity plays a very important role in many fields nowadays. And in this talk, I'll focus on some of the latest progress in numerical relativity, in particular for neutron-star merger and black hole formation in astrophysics. Okay, so this is a one-page summary of numerical relativity. So numerical relativity, as I said in the beginning, so numerical relativity is a field in which we solve the Einstein's equation, and also in the presence of matter like a neutron-star merger and stellar collapse, we also need to solve the hydrodynamics equation and the magnetic hydrodynamics equations. And also in the presence of a magnetic field, we have to solve the Maxwell equation. And also, so in numerical relativity, so many times we handle the very high density matter, in which neutrinos play an important role. And in such case, we also need to solve the neutrino transfer equation. And so blue shows that the current status, and for Einstein's equations, so method and numerical code are well established, in my opinion. And also nowadays, there are many good codes for handling the hydrodynamics and the magnetic hydrodynamics. also we have we know several important codes, but yes, there are many good codes. And also we have a very good in the world, all over the world, many good codes for solving Maxwell equation. And the last frontier is for handling the neutrino radiation transfer equation, because the equation for neutrino radiation transfer is Boltzmann's equation. So that means that we have to handle the 6-dimensional equation. So it's a very tough business, and so it's still not possible to directly solve the Boltzmann's equation. But nowadays, so there are several very good approximate solvers. So it's approximate solver, but it can capture the basic property of neutron radiation transfer. And so we have a very good code, and then also we have a Planck computer. And so high performance computer means that, for example, in Max Planck Institute, so in entire Max Planck Institute, we have a computing center, and it has a very powerful computer with more than 10 petaflops. So that implies that now we can perform a reliable numerical simulation to predict so high energy phenomenon in the universe.
When you say now, it means what? When you say now, it is possible to obtain.
Yeah, so in 2020 it's not possible, but so last decade it's very
10 years. When you say now, it means 10 years before.
Not 10 years before, it's very difficult. Basically, 10 years before, we didn't have any solver for this, for example. Also, we didn't have a good supercomputer, but after 10 years, so yeah, we have a significant development of a computer and Newton radiation transfer. And then, so maybe in the next decade, so this could be 10 times larger, and then so yeah, situation could be much better. So, but anyway, so right now it's possible to perform a reliable numerical simulation. Then I introduce about neutron-star merger. Why neutron-star merger is interesting? The reason is that neutron-star merger was predicted to be a promising source for short-half gamma ray burst, for which so we still didn't know the exact answer what is the progenitor of gamma ray burst. And also neutron-star merger was predicted to be a site, so promising site for R process nucleosynthesis. So R process means that the rapid neutron capture nucleosynthesis, for which we still don't know the exact answer. What is the site? So what is the main site for synthesizing the heavy element like gold and silver and plutonium and so on. And neutron-star merger was predicted to be a major factor since 1970s. Also, neutron-star merger was predicted to be a source for high energy phenomena, the so-called kilonova. And also, neutron-star merger is a variable site for studying nuclear equation state, because the neutron star is a high density matter, and this is a very good experimental site for studying the unknown nuclear properties like neutron scattering and the nuclear-neutron scattering and so on. And then what was nice that in 2070, so first neutron-star merger event was discovered. 17 was discovered. Then what was nice that this event shows that all the aspects for this question. Yeah. So this is one page, 2-page summary of the what was discovered in GW17. This is gravitational wave. So this is intensity of gravitational wave as a function of time, as a function of the time and in the frequency domain. So this clearly shows that the gravitational waves are detected. And also in this event, gamma ray burst discovered after the merger, binary merger, and also subsequently electromagnetic signals, in particular in the optical and radio and X-ray and detected significantly. So then, from this discovery, so for example, from this, so precise analysis for in the frequency evolution, so we can study the neutron star property through the tidal deformation of the neutron star in the cross binary. And also, this shows evidence that neutron star merger is a site portion of the gamma ray burst. Also, observation for the electromagnetic signals in the optical and infrared band show that this neutron star merger is the source for the kilonova. And this kind of observation has been still continuing. So in particular in the X-ray band and the radio band. So anyway, so in this event, so all these aspects was studied, and then in a sense, all these aspects confirmed by this event.
Masaru, do we know why the 2-second delay between gravitational evolution?
So perhaps there are two reasons. So after the merger, so it needs a time to launch a gamma ray burst. So typically, people believe that to launch a gamma ray burst, perhaps we need some enhancement of magnetic field or something like this through the turbulence. I'll talk about later. So for this, we need about 1 second, and also to penetrate the ejector. Then we need the time. So we have two reasons why 1.7 seconds are delayed. But anyway, this is a main discovery. So electromagnetic discovery in this event. So this is a kilonova-like curve. So this is time as a function. This is a flux as a function of time, and this shows the optical and infrared emission as a function of time. So I mean that in kilonova is predicted to shine in the first a couple of weeks. And actually, so this observation actually shows that such a shine after the merger. Also, in addition, in the X-ray and the radio band, this kind of the electromagnetic signals are discovered. So one is a kilonova, and the other is a synchrotron radiation by kinetic energy. So kinetic energy means that, as I said, that gamma ray burst launched in this event, and then this is naturally explained by the interaction between such a jet with interstellar matter. So this is in a sense, indirect evidence for the presence of gamma ray burst. So this is two major, in my opinion, two major discoveries in this event. And so in this talk, I focus on the early process nucleosynthesis. So this is also very good some tool for studying the neutron star merger and for getting additional information from neutron star merger event. Okay, so I talk about the neutron star merger and the nucleosynthesis. So as I said, that the neutron star merger is likely to be one major site for the process of nucleosynthesis. Here, so heavy means that the elements mass number larger than about 80. So 80 to 230 or something like this. This event shows that it could be a major site, but however, it is still not clear whether the neutron star merger is a dominant source of this element, and there are several other opinions which says that so it could not be the major site. And then I believe that the neutron star merger is likely to be the major site for the process event, but we have to show from theory side to prove that this hypothesis is the correct or not. And to prove this hypothesis, we have to reproduce observational fact. So one very important observational fact that we have an abundance pattern for this element in our solar system, and then such an abundance pattern in the solar system is called the solar abundance pattern. And so observational fact is that the solar abundance pattern is very similar to the abundance pattern in the metal poor star near galaxy and nearby galaxy. So this is called universality. So we have to reproduce this universality from theory side. So so as I said, that if a neutron-star merger is a major site for Alpha's nucleosynthesis in the entire universe, so this universality must be reproduced. For example, if we perform a numerical simulation, then we have to reproduce such a universality. So this is a solar abundance pattern of elements. So yeah, this is a mass number. So this is abundance fraction as a function of mass number. And in this talk, I'm focusing on the elements with mass number larger than 80. And for this region, there are two elements. One is a so-called S-process element, the other is R-process element. So S and R need the slow and rapid neutron capture. So R-process is R-process element. We need a very rapid neutron capture. Rapid means that in the presence of the neutron-rich elements, so beta decay soon occurs. So to get the R-process element before the beta decay occurs, so additional neutron have to be captured. But in the case of S process, so after the neutron capture, so soon beta decay. Then next neutron capture occur, but then beta decay. So this, yeah. Then these two processes are completely different, and in the R process, so we need a neutron-rich environment. Otherwise, so beta decay soon occur. And so this is a figure for universality. Here, so I'm showing some information related to the abundance of the elements, and this curve shows the curve from the solar abundance pattern. And the other point shows that the result for the metal poor star, galaxy and not galaxy, our galaxy and the nearby galaxy. And this shows that the abundance pattern is quite similar to each other. So all the results, observational results, fairly agree. So not fairly, very good agree with the solar abundance pattern. This is a so-called universality. So this suggests that this suggests that our process is likely occur on one type of event. Otherwise, it's quite difficult to reproduce this kind of universality. So then, the question is that whether neutron-star merger can reproduce this universality or not. So this is so in my talk, I'm going to talk about it. With a neutron-star merger, with some kind of neutron-star merger, it's possible to reproduce this kind of universality. Okay, so then this is does the neutron-star merger universality, and so answer is yes. So then I'm going to talk about latest investigation about this question. And anyway, so for this to answer this question, we have to perform a very realistic numerical simulation. So specifically, so realistic means that we have to take into account all the physics relevant. So physics relevant in this phenomena is that of GR and neutron radiation and NHG and so on. So we have to take into account such all the complicated physics, but now it's possible to do so. And this is just a demonstration of what it's possible. This is a latest numerical simulation in my group. So this is GR radiation magnetic simulation in GR. And so after the merger of neutron-star, so initially we have a massive neutron-star, but eventually it collapsed the black hole. And also associated with the merger, we have this, and we have mass ejection sensor. So we can now perform this kind of simulation. And also what is important is that I believe that this kind of simulation has a predictability. And but the situation is not very simple. So because there are many variety of possibility in the neutron-star merger, neutron-star merger, and black hole neutron-star merger. So in the last decade, many simulations have been performed with a simplified assumption. So simplified assumption is that we don't take into account the Newton transfer and the magnetic field effect and so on. But we can at least qualitatively understand what happens after the merger of neutron-star. This is a summary for the possible fate of a neutron-star merger. So anyway, so there are, broadly speaking, there are two possibilities. If total mass, so this then is larger than some critical mass, so after the merger of neutrons, black hole is formed. And if the mass difference, significant mass difference is present, in such case, this is formed because after just before the merger, tidal force play an important role to form it. But in the absence of the mass difference, so simply black hole is formed. On the other hand, if mass is not very high, so in that case, so at least temporarily, very massive neutron star, so that's so-called hypermassive neutron star. But the hypermassive neutron star eventually collapses to a black hole because it's very massive and due to the cooling and angular momentum transport. So because after the merger, it's rapidly already. So this is one of the important elements to sustain the gravity of a massive neutron star, but after the transport of angular momentum and the loss of angular momentum by gravitational waves emission, then it eventually collapses. But due to the angular momentum transport before the collapse, usually we have this like this. Also, if mass is very small, in such case, long lived, so almost infinite lifetime, not infinite, but very long time, lifetime neutron star is formed. Anyway, so there are many possibilities. This was this was information from many numerical-relativity simulations in our community. But the question is that there are many possibilities, and also there are many channels to eject matters from this system, and so such ejected matter eventually can be observed. And then so we can find a nucleosynthesis evidence or something like this. So, but the presence of many possibilities in the presence of many abundance patterns of nucleosynthesis. And then so we have to investigate all the possibilities. So when we are interested in the nucleosynthesis result. Also, we have to also consider the black hole neutron star dynamics. So in this case, fate is very simple. So neutron star is not tidal disruptive or simply tidal disruptive. In the absence of tidal disruption, we have only black hole, so no mass ejection and no nucleosynthesis. We don't have to consider this case in the nucleosynthesis investigation. Yeah, so by contrast, in the presence of tidal disruption, again, we have a tidal disruption, disk and mass ejection, and so on. Also, in addition to binary neutron star merger, we also have to explore what happens to black hole neutron star dynamics when we are interested in the nucleosynthesis.
So I have a question. In this and previous scenario,
Yeah.
Up to so the mass in this,
Yeah.
how significant can it be? Are we talking about 10%? So there's a this point.
Yeah.
Here and how massive can this be?
So yes, so it depends on the black hole mass and the black hole spin. And so anyway, to get the tidal disruption, mass of black hole should be not very high. Otherwise, tidal force at the innermost state of circular orbit is very weak. So typically, so mass has to be smaller than the 10 solar mass or something like this. And also, black hole spin is high. So location will not most state. Then so tidal disruption is more subject. So that means that a mass so depends on these parameters. And so yeah, but so typically about 10 to minus 2 to 10 to minus 1 solar mass. Of course, 0 is possible, so it's wide range. Yeah. Anyway, so all these information have to be studied in numerical-relativity.
Question?
Yes.
Second scenario.
Yeah.
The gravitational radiation is very low, right?
So yeah, not very low, but after the tidal disruption, gravitation will shut down quickly. Yeah. For this case, so wave form is very similar to the binary black hole case. But for this case, in the middle of a sharp signal, so gravitation is sharp. But still, so this occurs very close orbit, and then so usually very close orbit, not far orbit. Then so gravitational amplitude is not very small. It's fairly large. So then anyway, so yeah, in the presence of disk or tidal disruption or merger, so we could have mass ejection. This is a result from the many numerical simulation. But there are 2% steps for mass ejection. First step is a dynamical ejection. This occurs by shock heating or tidal effect. In the presence of black hole, in this case, only shock heating, not only tidal effects are important. This procedure in 10 milliseconds after the merger. And in addition, we have another channel for mass ejection. As I said, so after the merger, we typically have a compact object surrounded by this. So in such case, from this, mass ejection can occur. So through the magnetic hydrodynamics effect or so viscous braiding effect. So we call such a mass ejection post-merger mass ejection. And this occurs spending a long time, so typically 1 second. A long time is 1 second, very long in this field. And also, so anyway, so we have two mass ejection channel, and also another mass ejection channel is the gamma reverse. But for the nucleosynthesis, people believe that these two mass ejection channels are very important. And as Vito pointed out, so ejecta mass and the disk mass are very important for this kind of study. But so what is another? So we have another important parameter. So the other important parameter is the so-called electron fraction. This is defined by the proton number density divided by proton neutron number density. This shows that the anti-neutron richness, if Y is large, so then the neutron richness is low. But Y is small, so neutron richness is high. So if Y equals 0, so proton fraction is 0 and the neutron fraction is unity, so then so it's very neutron rich. So in typical neutron star, this value of Y is 0.05. So it's neutron star is neutron rich. This is the reason why so neutron star is very important for synthesizing the process heavy element. And anyway, so this Y is so then another important thing is that Y is controlled by weak interaction. So because these two elements are related by the beta decay, so then so weak interaction play also very important role for studying a nucleosynthesis. So this is one very clear evidence that Y is very important. So this is so one of the results for the nucleosynthesis calculation by Wanado many years ago. And he showed that he performed a nucleosynthesis calculation changing this Y. And so this shows that if Y is small, for example, 0.09, it's very small. In this case, so mainly element with a mass number very large. Very large means that 200 and 150 is synthesized. But by contrast, if Y is close to 0.5, 0.5 means that like a helium and carbon and oxygen. In such case, so here only the low mass number elements are synthesized. So this clearly shows that to synthesize the heavy process element, we need a low value of Y. By contrast, if we would like to synthesize only small number of heavy elements, so like 100 or 50 mass number, then so Y value should be 0.3 or 0.4. This is a very important information. Please remember, in the following discussion, it's very important. And so, as I said, that there are two types of the mass ejection channels. So one is a dynamical mass ejection, which occurs within the 10 milliseconds after the merger. And for this, so many numerical-relativity simulations have been done so since 2013. And then I think that it's well understood. Fact, we have learned that mass of the ejecta is between 10⁻⁴ to 10⁻² solar mass. So at most 1% of solar mass. And the other important fact is that in the case that mass neutron star formation is formed, in this case, total mass of binary should be small. In such case, ejecta mass is not very large. So even in the case that mass is fairly large, in such case, but not black hole is formed. In such case, only in such case, mass of dynamical ejecta is very large. And the other important discovery is that the electron fraction is low. Low means that between 0.05 to 0.4. So this means that this dynamical ejecta is suitable for nucleosynthesis of the phase element. This is not relevant. And we have the other mass ejection channel. So the other mass ejection channel is post-merger mass ejection. This is much more complicated. So for studying the dynamical mass ejection, we just perform a collision, then mass ejection. It's easy. But post-merger mass ejection proceeds spending about 1 second, and the physics is much more complicated. So anyway, so neutron-star is usually we believe that magnetized, and the remnants are magnetized. So that means that we have to take into magnetic field to study this process. And then, and also after the merger, we have a neutron-star disk, but it's usually differentially rotated. And in such case, so we know that MH instabilities occur inevitably. And then magnetic field is amplified, and then eventually, so turbulence is excited, and then so effective viscosity appears. So then, so effectively, system evolves due to viscosity. And also, in the presence of very strong magnetic field, so purely NHT effect, like magnetic-centrifugal effect. So in the presence of global magnetic field with a rotation, magnetic field line rotate like this, and then so matter is ejected. So such a complicated dynamics is relevant for post-merger mass ejection. So in the last couple of years, so many simulations have been done, and then so our understanding is getting better and better. And then so this is one page, one sentence result. So anyway, so post-merger ejecta mass depends strongly on the central orbit. In the presence of very long-lived neutron star, so ejecta mass could be very high. So as Vito asked, so after the merger, in the presence of after the merger, in particular the long-lived neutron star formation, disk mass is about 20% of the solar mass. Then, in the absence of black hole, so such a matter does not fall into the black hole, does not fall into the neutron star, and many large fractions can be ejected from the system. But by contrast, in the presence of a black hole, so if black hole is formed soon, so many of matter fall into the black hole. Then, so matter mass ejection becomes small. This is very important. And the other important thing for the ejecta is that YE. So then, so the central focus in this community is that to determine the YE accurately. So then, so we have so many people perform the simulation. I believe that now, so our understanding is much better than 5 years ago. So then, so I would like to talk about how the Y is determined in the mass ejection. So this is a basic, this slide shows the basic evolution process of disk by Newton cooling and viscous stability. As I said, that after the merger of neutron star, black hole, neutron star, typically we have a black hole neutron star plus disk. And then so mass ejection occurs from the disk. And so then the question is that how disk is evolved. So as I said that after the merger, so magnetic field is amplified, and then so viscosity is effectively produced due to the turbulence, energy turbulence. And then in such a system, so due to the viscosity, angular momentum is transport, and then so disk expands rapidly. In addition, in the presence of viscosity, we have viscous heat. However, temperature is very high initially. And then, so in such a, if the temperature is higher than several MeV, then neutrino luminosity is very high. So in such case, so even if heat are generated by viscosity, neutrinos escape, so carry such heat. And then so viscous heating cannot be used to mass ejection. However, so because the angular momentum is transported and then this expand gradually. And that means that the density gradually decrease like this. And then so due to the adiabatic cooling, temperature decrease. And then eventually neutron luminosity decrease because of neutron luminosity is a still function of a temperature. So typically, so neutron luminosity is proportional T to 6. Then so if temperature decreases a little bit, then so neutron luminosity decreases significantly. And then eventually, so viscous heating is much larger than neutron luminosity, and then so viscous heating is fully used for later expansion and mass ejection. This is a basic scenario for the mass ejection from disk. And for this time scale is very long. So very long is that time scale is 1 second. So in the case of a dynamical mass ejection, time scale is only 10 milliseconds, but for viscous evolution, it's 100 times longer. So this means that numerical simulation is more difficult. We have to perform a longer numerical simulation. But now it's possible to perform such a simulation. And then let me show that what is the mechanism. So this is animation for a black hole plus this. So 3 solar mass black hole with spin parameter 0.8 and 1.1 solar mass this. So this is rest mass density, temperature, and entropy, and y. So let's focus on this slide. Yeah, density and electron fraction. Yeah, so anyway, so initially we have some relaxation phase, but after that, due to the angular momentum, so angular momentum transport, this expand gradually. So initially simply so such a gradual expansion occur, but at some point the temperature decrease and the neutron luminosity decrease. And then so viscous heating play an important role, and then so mass ejection occurs. So you can see the mass ejection from now. Yeah, mass ejection occurs. This is due to the decrease of the neutron luminosity. And then so this mass ejection continues for a long time. Yeah, this is a basic scenario for the post-merger mass ejection. And the next question is that how large is the electron fraction? So initially, well, electron fraction is very low because it's a neutron rich and dense. However, so after the expansion of disk, Y becomes gradually low. So the reason is very simple. So in this phase, so beta equilibrium is established, and in such case, so electron is highly degenerate, and then so due to the high electron degeneration, so neutron richness is enhanced, and then so Y is very low. But after expansion, density decrease, and then electron degeneracy decrease, and then so neutron richness decrease, and then so this color change to the 0.2 and 0.2 and eventually at the mass ejection, this is a mass ejection phase. So yeah, typical value of Y is 0.2. Yeah.
Going back to the theme of today's question, could you recover the same basic physics if you just said the background is curved and just solve viscous hydro? It would basically be the same story.
Yeah, that's the same thing. Yeah. Oh.
No, that was
Yeah.
why you are increasing the electron fraction?
Yeah, so maybe so.
Okay.
Yeah, so then okay, so I will change to the next slide. So anyway, so initially density is very high. So that in such case, weak interaction time scale could be much shorter than disk evolution time scale. And in such case, beta equilibrium is established. So that means that so chemical potential has this relation. But now, so density is very high. So then, so well, this chemical potential electron essentially completely determine this equation, because this dominates over the other chemical potential. This is essentially zero, and this is the chemical potential is much lower than this electron chemical potential, so like this. Then, so if because this is very high, so then so this should be comparable to this one, and then this should be small. This is a reason. So if in the high temperature, neutron richness is achieved. So the reason why neutron star is neutron rich is that because density is very high and chemical potential of the electron is very high, then so neutron chemical potential should be comparable to the electron chemical potential. This is the reason why in high density, so electron fraction is well, neutron richness is high, Y is low. So this situation doesn't change even density slightly change. So if density slightly change, so this inverse direction disappears because the interaction of the neutrinos are weaker. But still, if we have either higher temperature and higher density, we have this kind of reaction, and still this equilibrium is established. But after density decrease, our temperature decrease below 3 MeV. Then so this interaction completely decaps. Then in such phase, so we have some data equation, but after this T max decrease below 3 MeV, this is preserved. So in such point, electron fractions determined, and then so as I showed in the previous slide, so at the decoupling of the interaction, so equal value of Y equals 0.3. So this is, I think that I think that at least in Germany, so because he's German, so we are in Germany, so we have consensus. So then anyway, so in this, so that means that post-merger ejecta doesn't have a very high neutron richness, so equally neutron richness. So as I said in the previous slide, if Y is 0.3, so it's not possible to synthesize a heavy element. And so that means that from the post-merger ejecta, it's quite difficult to synthesize the heavy element. Actually, so yeah, this is a summary of our study in the last 3 years. So this shows the electron fraction, the histogram of the electron fraction for 2 cases. For this case, so long-lived neutron star survive. And this case is a neutron star is a short-lived black hole. So soon that in the 20 milliseconds after the merger. And so this is a high mass case, and this is low mass case. In high mass case, as I said, that this is the dynamical ejector, and this is the post-merger ejector. In high mass case, the dynamical ejector could be larger than this case, so low mass case. By contrast, in the presence of a black hole, post-merger ejector is suppressed due to the absorption of the black hole. And in this case, post-merger ejector could be fairly high. So this means that for this case, so Y component is suppressed, but high Y component is enhanced. For this case, low Y component is or both components are so that means that so this means that our nucleosynthesis abundance pattern becomes something like this. For long-lived neutron star case, so because of the presence of a huge amount of the high Y element, so relatively low mass number elements are predominantly synthesized, but by contrast, so heavy elements are suppressed. This dot shows the solar abundance. But by contrast, in the presence of short-lived mass neutron star, the black hole, so abundance pattern becomes very similar to the solar abundance pattern. So the reason is, as I said, that for this case, we have too much post-merger ejecta because in the absence of black hole. But in this case, yeah, the ratio of the 2 components are very good. So very good blending 2 components is achieved for this. So then, so this is a prediction. So as I showed, only in the case that remnants of a binary neutron star merger collapse the black hole in a short time scale after the merger. So we don't have the so long-lived neutron star universality can be reproduced. So I mean that only for this case, abundance pattern is a very good fit with the solar abundance pattern. So that implies that suppose that binary neutron-star merge as a main site for the other process nucleosynthesis, then so long-lived massive neutron star should be a minority. If this is a dominant channel, so we never have the get the solar abundance pattern. We cannot have. So this suggests that short gamma ray burst from remnant magnetar. So this is one of the very popular scenario for short gamma ray burst. But this should be minority. So magnetar formation should be minority. So magnetar means that strongly magnetized the long-lived neutron star. So if this is a majority, so solar abundance pattern cannot be reproduced. But in other words, in case that many long-lived neutron star formation are observed in the future, then so neutron star merger scenario for the alpha nucleosynthesis may be excluded. So this is a prediction from purely numerical-relativity. But so yeah, but this kind of work was done with a two-step simulation. So we have been performed a merger simulation and post-merger simulation separately. I think that is okay. But so for more self-consistent treatment, we need to perform a simulation. So just from the merger to the post-merger mass ejection self-consistently in one simulation. However, so time scale is fairly different. As I said, that the dynamical mass ejection time scale is only 10 milliseconds, but the post-merger mass ejection time scale is 1 second. And also, in addition, we like to reproduce a short gamma ray burst. But typical time scale of short gamma ray burst around 2 seconds. So it's very challenging to perform such simulation. But now, so it's possible. So what I mean that is that for consistent study, so a simulation of inspired to post-merger is more than 2 seconds is required. This is a milestone goal for the community of numerical activity. But now, so it's possible to do. So also we have to take into account the complicated physics. But now it's possible to do, at least for the black hole neutron star merger. The reason is that for black hole neutron star merger, time step and grid spacing of a simulation is approximately proposed to black hole mass. So that means that black hole mass is fairly large, so 5 solar mass, 10 solar mass. In such case, so computational cost is much lower than the for the case of binary neutron star mass. And now it's possible to do. And actually, so recently, so one of my students performed such simulation, and I would like to introduce a very nice animation. This is animation for density, magnetic field strength, and the ratio of the magnetic field energy density to reference density, electron fraction, temperature, and entropy per barium. For the case of the black hole mass is 5.4 solar mass in the black hole spin, 0.75, and neutron star mass is 1.35. So we performed a simulation for 2 seconds for this case. And this is a snapshot with X and Z plane. And Z is just a rotational axis of black hole. Yeah, anyway, so after the simulation, so neutron star is finally disrupted, and then initially dynamical mass ejection occurs. This green shows that neutron richness is very low, and so this shows the neutron rich matter is ejected from the initially. So this is a dynamic mass ejection. And subsequently, so disk is formed, and the disk is highly magnetized. And then, so due to the turbulence and effective viscosity, disk gradually expands. And also, due to the magnetic field enhancement, we can see that the pointing flux generation along the axis of the black hole. So this could be a good sign for modeling the short gamma ray burst. And then so this gradually expands, and then so neutrino and also temperature decrease, and eventually neutrino luminosity decrease, and then mass ejection occurs. So this is good. So entropy is higher in the viscous heating is efficient, and then so in the high viscosity, high entropy region go out. So this shows that mass ejection is occurring for this phase. And then so this continues for a long time, so more than 2 seconds. Maybe we can skip through. Gradually density decrease, temperature decrease, but then you see mass is ejected, and still we have a pointing flux in the first 2 seconds. Anyway, so this kind of simulation is not possible. So this is a summary for evolution of electromagnetic energy and ejecta mass and neutron luminosity. So just focus on the ejecta mass and neutron luminosity. As I said, for many times, so we have 2 steps. One is dynamical mass ejection, and the other is a post-merger mass ejection. This is clearly seen in one simulation. And also, neutron luminosity curve is something like this. But here, so neutron luminosity quickly drops. This time agree with the post-merger mass ejection. So this clearly shows that post-merger mass ejection occurs after the neutron luminosity drops, or temperature drops. This can be is proven in just one simulation. Also, this is electron production. So we have 2 components, dynamic ejecta and post-merger ejecta. So this agrees with previous prediction by 2-step simulation. And in such case, we can also reproduce the approximately solar abundance pattern. And this is the maybe final animation. It's interesting. So after dynamical tidal disruption, disk is formed around the black hole, and in the disk, magnetic field is amplified. This is a magnetic field strength. And then, so after a couple of 100 milliseconds, so then magnetic field line penetrate along the rotation axis of black hole, and it looks like some gamma ray burst from the this system. So anyway, so this kind of simulation is not possible. Okay, so I'll skip everything after that. Anyway, so finally, I would like to conclude. Numerical relativity is playing an important role in predicting the latest observational results, in particular gravitational-wave and its electromagnetic counterpart. And as I emphasized, simulations are relevant physics, not physics. So this means that numerical relativity has a predictive power. And as I already said, one prediction from our latest numerical simulation is that neutron-star merger, formation of a long-lived neutron-star magnetar would be minority. Otherwise, so abundance pattern cannot be reproduced. And I have another prediction, but I skipped. But anyway, so more prediction will be done in the near future because our computational resources are good, and we have a very good tool, good numerical relativity. So that's all. Thank you. Thank you very much.
You have questions? I think David was requested.
In the build-up to your first prediction, you said there's a consensus in Germany.
Yeah.
So that raises, I think, 2 obvious questions.
Yeah.
The first is, how independent are the tools being used, that were used to give that consensus? Is it the same code being used by those 2?
No, completely different code. Completely independent code, but also weak interaction is highly complicated, and so we don't take into account all the relevant weak interaction. And also, for example, neutron transfer is very approximate, and 2 codes are completely different. For example, in the neutron transfer and the weak interaction, so but result of what's
And so
also their also their simulation is based on Newtonian, pseudo Newtonian. And this is the fully
so maybe related to that. Are there any simulations? Are there any groups which don't get the same thing?
Yeah, so perhaps now, so we understand that for this kind of a simulation, taking into account all the relevant weak interactions is very important. If we neglect some of weak interactions, so we could have buttons. So this is in a sense, our finding in the last couple of years. So anyway, so in particular, so NPA groups in Garhin perform the detailed simulation, changing the weak interaction input, and then so they clearly show that taking into account the important weak interaction process is very important for this kind of stuff. Gravity are not very important, so weak interaction is very important in this case. Yeah, sorry.
Yeah, so I actually have two questions. The first is, I thought that for some GRBs, the Lorentz factors were very large. Can you get large Lorentz?
No, it's quite difficult. So
It's very big, you need a very high temperature or something, right?
I have a reason. So we have the reason. So it's impossible to reproduce a high Lorentz factor in this kind of simulation.
So
the reason is that we perform magnetic hydrodynamics simulation.
So you need 5 million cells. So what's the limit? What's the Lorentz factor, which we can get accurately with at the most 10. Yeah, but that's in 10 to 3.
Yes, it's impossible. So in the MHD simulation, the reason is that in MHD simulation, so we have some maybe it's a bit technical, but for solving the hydrodynamics equation, we have some primitive recovery. So primitive recovery means that we solve the 3 momentum in GR, but we also have to determine the force U0, UT. So we have to determine UT from the determined UI. So in this process, so if magnetic field strength is magnetic energy density is lower or comparable to the resonance density, so we can perform a very accurate simulation. But if magnetic field strength, magnetic field energy density is say about 100 times larger than resonance density, it's essentially force-free region. So it's impossible to perform an accurate numerical simulation. Yeah.
And my second question is related to this claim about the nucleosynthesis, the relative abundance. Your conjecture number 1, well, your statement, conclusion number 1, is based on a very specific set of initial conditions. So are your stars magnetized, for example?
Yeah.
I mean, have you swept? So my question is, how do you know that you swept the range of possible conditions for the neutron?
Yes. For example, so we changed the mass of neutron stars initially, and then so conclusion same. So in the latest paper, so we performed the 5 simulation changing the mass and the mass ratio, and then but the conclusions are same. Yeah.
When you talk about our process, you involve the reactions that many of them, I guess, are theoretical. There are no, there are a few experiments that you can say that try to measure the percentage of precision and look at the percentage of the involving in our process. Is this taken into account or for the moment?
You're right. So actually, so the cross section of a reaction are uncertain, highly uncertain. Okay. So then so so for example, if we change the, I'm not the expert for this. So actually, so this guy is my collaborator, so he's the expert on. So if we change the, for example, there are many tables, a couple of tables. If we change the table, so result change. Sure. So
but
then,
change dramatically or
so not dramatically. So for example, so we have this kind of abundance pattern. so for this could be slightly change if you change yeah. So that means that in this kind of calculation, yeah, we don't have a quantitative accuracy.
So in the future, they can be measured on the lab and can
Yeah.
perform better.
Yeah.
The second one is about magnetic field.
Yeah.
If you've got a star, then you know, and get the reality, the next body is some kind of new field theory that if I think a star, that can be, dynamo.
Yeah.
The thing is very complicated. Or I imagine GR is even more complicated. How is that? Some kind of new field theory that
You're right. So yeah, so in the viscous hydrodynamic simulation, we just input the result for the study for disk. So there are many disk simulations, and this shows that our enhancement magnetic field and the diagram is excited, and then so effective viscosity can be expressed by alpha viscous prescription, and then so we input such a you're right. So eventually we like to perform a simulation we like to perform the first principle simulation. So with a magnetic field, but at least with effective viscous prescription. So and also I should emphasize that. So I talked this simulation finally. So this is just magnetic hydrodynamic simulation.
Okay.
And in this simulation, we believe that at least approximately, dynamic process resolved. Of course, not perfectly, not perfectly, but at least approximately.
So we don't have much time, so you can start.
Yeah, okay, one simple question. When you talk about the universality of the solar abundance, you mean this is the ratio between the high mass elements? Because when in astrophysics, we always talk about metallicity, and metallicity, low star, low metallicity, high metallicity, but that's the comparison with hydrogen, or why what's the...
Oh, so so universality is just so how good is the solar abundance pattern to be produced?
Yeah, but you mentioned at the beginning that you were using it for many different stars.
Yeah.
Nearby galaxies.
Yeah.
So how my question is how universal is that? Because we do sometimes talk about different metallicity, but I guess when we talk about metallicity, that the ratio with hydrogen.
In this case, metallicity is very low. So for all the samples, metallicity is 10⁻⁴, less than 10⁻⁴.
Okay, so it's always
it's very low. So only for low metallicity stars, we have this one. So pollution by other processors, for this stars, pollution by other processors assuming to be very minor. So then, we believe that in such stars, only by some event for which synthesize our process only pollute this star. This is the assumption.
One last quick question.
You said you change the parameters of the initial condition from.
Yeah.
But for each set of parameters, how many realizations do you make? So there is a random component in your initial condition. So how many realizations do you make? How many? I guess you have a random initial.
So this is not. This is completely different from cosmological simulation, something like that. Yeah. We don't have any random. So because the neutron star. So we believe that neutron star simply evolved by the radiation reaction of gravitational wave and eventually merged. No other process is relevant before the merging. So usually we believe that so we can determine initial condition for simulation if we specify the mass of two neutron stars and the equation state. So parameters are highly limited. And then in this case, we just choose a couple of masses of neutron star and we change the equation state. So this is just important parameter.
Because in the movies you show, you can see that there is a random component. So where does it come from? From it's actually numerical.
Random component.
Well, you show a couple of movies in which you see that there is symmetry of problems.
Which ones?
Yeah, example there. You see that it doesn't look like a completely smooth.
Yeah.
So what does it come from?
This is just a model simulation. So this is the reason why I said that I need a self-consistent simulation. So for this simulation, so we initially prepared very well symmetrical initial data, but it's just a very simple model for post-merger system. So this is a reason why we need a self-consistent simulation eventually like this. Yeah, so in the last part we show that the animation for self-consistent. So eventually we need this kind of simulation for the system, but until quite recently it was impossible to do because of the limitation of computational research. But at least this result of this simulation so suggests that so two-step simulations are okay to understanding basic physics. Yeah.
Thank you. Well, I'm afraid we ran out of time, so let's thank our speaker.
Yeah.